This is our video on prime numbers, relatively prime numbers, and we'll also be looking at the method of proof by contradiction and greatest common divisors. So, starting with prime numbers, a prime number is an integer p greater than 1 whose only positive divisors are 1 and p. So, for example, 2 is a prime number because the only positive divisors of 2 are 1 and 2. And if we look at the first few primes written in order, we get 3, 5, 7, and so on. If you take a larger number, for example 3041, and ask whether or not it's prime, checking can be a little bit harder. You could use the definition, which would mean that we would check the numbers from 2 through 3040. These are the numbers, the positive numbers different from 1 and 3041, and see if any one of them is a divisor of 3041. But that would be sort of a tedious calculation. There are various ways to shorten the calculation if you're going to do it by hand. For example, as we'll see in the exercises, you only have to check the integers between 1 and the square root of 3041. So if you check the integers 2 through 56 or 2 through 55 and find that none of those is a divisor of 3041, you will have shown its prime. There are also prime checkers online. These are websites you can go to, type in a number, and the program there will return a yes or a no, prime or not prime. 3041 is a prime number, by the way. And now we look at some simple examples of non-primes. Why is 14 not a prime number? It has a positive divisor other than 1 and 14. Namely 7. Why is minus 7 not a prime number? Well, minus 7 is negative, and one of the requirements, if you look at the definition, one of the requirements of being a prime number is that it has to be an integer greater than 1. And 3/4 is not a prime number because 3/4 is not an integer. Now, if you take a pair of numbers, there's a concept of a pair of numbers being relatively prime. And in order to discuss that, we have to talk about common divisors. So I'm not sure this phrase needs defining, but a common divisor of two integers, a and b, is an integer k which is a divisor of both a and b. I haven't really said much more there than k is a common divisor. And any two integers have at least two common divisors. They are 1 and minus 1, as is pretty easy to check. So here now is the definition of relatively prime for two integers. A and b are relatively prime if they have no common divisors greater than 1. In other words, if the only common divisors of a and b are 1 and minus 1, then they are relatively prime. So a few examples. 6 and 25 are relatively prime. I have checked this the hard way. I've used the definitions, so I've written down the divisors, the positive divisors of 6, 1, 2, 3, and 6. And I've written down the positive divisors of 25, 1, 5, and 25. And the only common divisor is 1. So the greatest common divisor, the largest common divisor, is 1. 91 and 35 are not relatively prime because there is a common divisor, 7, which is greater than 1, a positive common divisor, or a divisor greater than 1. Okay, so here is a lemma that will be useful in some of our later work, and it will give us an example of a proof technique that we also want to discuss in this video. So the lemma is, for all integers a and b, if a and b are relatively prime, then so are a minus b and b. So to take a quick example, the integers 12 and 25 are relatively prime, as we verified earlier. So what would the lemma tell us? It would tell us that the two integers 25 minus 12, or 12 minus 25, and 25 are relatively prime. In other words, the lemma tells us that minus 13 and 25 are relatively prime, which is easy to check. And now we're looking at a proof of the lemma. So we're proving for all integers a and b something happens, and that something is that if they're relatively prime, then so are the two integers a minus b and b. So we start in the usual way, assume a and b are integers and that a and b are relatively prime. And a quick sentence describing what we have to prove. We have to prove that a minus b and b are relatively prime. And now we translate into equations that is possible. But first, a quick discussion of the details of the method we're going to use. We're going to prove a minus b and b are relatively prime by making the assumption that they're not relatively prime. And then, based on this assumption, we're going to prove something contradictory. And it will follow that it's impossible that the statement a minus b and b are relatively prime is false. So it must be true. And we will discuss this method in more detail later in the slides. So this is known as proof by contradiction. So starting the proof, toward a proof by contradiction, assume that a minus b and b are not relatively prime. So the plan is, from that assumption, we want to derive some statement that's contradictory. This is what we can translate into equations. The assumption that a minus b and b are not relatively prime tells us that they have a common divisor greater than 1. We're going to call it d. And that means that d is a divisor of a minus b. So a minus b is d times some integer k1. And d is a divisor of b. So b is d times some integer k2. Okay, couldn't fit the proof all into one slide, so it's continued on this slide. So just a summary of where we are. We know, because we've assumed that a and b are relatively prime integers. And we know there is an integer d for which a minus b is d times k1 and b is d times k2, where k1 and k2 are integers. So this is the summary of the previous slide. And we want to prove something contradictory. So the plan is to add the last two equations. The equation a minus b equals d times k1 and the equation b equals d times k2. And if you add without doing any simplifying, the left-hand sides give you a minus b plus b, and adding the right-hand sides is d times k1 plus d times k2. And now we simplify. The left-hand side simplifies to a. On the right-hand side, we can factor the d out. A is d times k1 plus k2. And now, as shorthand for k1 plus k2, we use k3. So a is d times k3, where k3 is the integer k1 plus k2. As usual, we know k1 plus k2 is an integer because the integers are closed under addition. So d, in addition to being a divisor of b, right, that was one of our assumptions up here, is a divisor of a. So a and b are not relatively prime because they have a common divisor greater than 1, and this contradicts the what we know, because we assumed it, that a and b are relatively prime. And now we want to look in a little bit of detail at the method of proof by contradiction. Going to try one more example. So we're going to prove that for every real number x, the fraction 2x minus 3 divided by x plus 7 is not equal to 2. So assume x is a real number, and we're going to prove that this fraction 2x minus 3 over x plus 7 is not equal to 2 by contradiction. So we assume that statement is false, which means we're assuming that 2x minus 3 over x plus 7 is equal to 2. And now we have something positive to work with. We have this equation, and we know how to work with equations. So we're just going to do the natural operations here to simplify. We're going to multiply both sides by x plus 7 to get 2x minus 3 is 2 times the quantity 2x plus 7. I'll multiply through by the 2 on the right-hand side and subtract 2x from both sides. So going from this equation to the equation minus 3 equals 14 involve two easy steps. And minus 3 equals 14 is not possible. This is a contradiction. So our conclusion is that 2x minus 3 over x plus 7 is not equal to 2, because we arrived at a contradiction by assuming that it was. Sorry. Okay, so here's the principle restated in sort of general terms. If you want to prove a statement P by contradiction, you assume that P is false. So that means you're adding the negation of P, the statement that P is false, to your assumptions. And then using that and other assumptions, you prove any contradictory statement. And the idea is, if the assumption that P is false leads to a contradiction, P can't be false. It must be true. And now a few notes on how and why this method works, and some of the details of how you should do it. When you begin a proof by contradiction, with the assumption that the statement P is false, you should somehow alert the people reading your proof to the fact that you're doing a proof by contradiction. So, for example, you could say, we will prove P by contradiction. We assume, therefore, that P is false. Or you could say, toward a proof by contradiction, assume P is false. Some way of alerting your reader to the fact that a proof by contradiction is beginning. And the contradictory statement that you prove can be something known to be false, like 0 equals 1 or minus 3 equals 14. Or it can contradict one of your assumptions, which is what happened in the first example proof we did. Proof by contradiction works especially well for proving negative statements, because when you assume a negative statement is false, you get something positive to work with. So if you see some negative words in a statement you have to prove, that might be a signal that proof by contradiction would work. So looking back at our first example, we assumed A and B were integers, and we proved the if-then statement. If A and B are relatively prime, then A minus B and B are relatively prime. So I'm just calling these two statements R and S for short. So we did this by assuming R and then proving S by contradiction. So we assumed S was false, and the contradiction that we arrived at was that R was false. So basically the proof consisted of assuming S was false and showing R was false. Well, assuming S is false and proving R is false is really proving the statement, if S is false, then R is false. And this is a valid way of proving an if-then statement, and it's really just a special case of proof by contradiction. So here's what I mean. If you want to prove R then S, if R then S, it's enough to prove that if S is false, then R is false, which is essentially what we did on our first example. And this is called proving the contrapositive. And the statement, if S is false, then R is false, is called the contrapositive of if R then S. See, there was a typo here in this first quoted statement, but it's now repaired. So now we're going to talk about change subjects just a little bit. We're leaving proof by contradiction, and we're going to look at another way to say that two integers are relatively prime. And in order to do it, we have to talk briefly about greatest common divisors. So if A and B are two integers, and at least one of A and B is not 0, then the greatest common divisor of A and B is the integer d for which, and now I simply want to say that d has to be a common divisor of a and b, and that d has to be the greatest. I've split this into two parts. So first of all, d has to divide a and divide b. This is the part that says d is a common divisor. And secondly, the part that says that d is the largest of the common divisors. For all integers c, if c is a divisor of a and a divisor of b, then c has to be less than or equal to d. And this sort of a long phrase, so it has a shorthand. The greatest common divisor of a and b is usually written GCD of AB. And a few examples. When we showed that 6 and 25 were relatively prime, we showed that the greatest common divisor was 1. And for 91 and 35, the largest of the common divisors is 7. We didn't do this calculation, but I have done it. Oh, and here it is. The positive divisors of 91 are 1, 7, and 13. And 91. The positive divisors of 35 are 1, 5, 7, and 35. 1 and 7 are common divisors, and 7 is the largest of those. So, how do you say A and B are relatively prime? Using the greatest common divisor terminology. The integers A and B are relatively prime if and only if the greatest common divisor of A and B is 1.